Hey there! Again, I am here with one more interesting question related to computer organization and architecture course. Let's review the instructions of the exercise. As you see, we are given hexadecimal values, 15 hexadecimal values, which represents 15 assembly instructions. So, what should we do? We should convert these hexadecimal values to binary values. After that, we should take these binary values and follow some patterns that I will share with you. And after following that patterns, we'll get assembly code. All right. And this is called reverse engineering. After completing, finalizing this reverse engineering, we'll look through code, we'll do some analysis and etc. So let's start and not lose our time. Uh, so These are patterns that will follow, and I will explain during converting. So let's start. Initially, we are given this 8 digits hexadecimal value. Each of them, each digit character of this value represents 2 to the power of 4. Uh, I mean, uh, let's say not 2 to the power of 4, let's say 4 binary representations, digits, all right? So even we don't need to use any additional tool, just we'll take one digit and convert it to decimals, and after decimal, converting it to binary. For example, E represents 14. What is 14? 14 is like this. 3 represents 3, so 3 will be like this. A is 10, so it will be like this. 0 is 0, 1 is like this, and 3 zeros. You see, it is easier. So if you're a computer science student, you should be able to convert this, all right? So initially, we get this value, all right? Now, we should follow some pattern to convert it assembly code. What should we do initially, all right? First of all, we should pay attention 2 digits after this 4 bits. I mean this part. All right. If it's 00, it means this operation will be data processing operation. And the first 4 is represents conditional type, so this will be unconditional. By the way, it is not required to know them by heart, uh, but over time you are working, you will memorize them, you will know them by heart, all right? There are tables that you can refer, all right? So next, since it's data processing, we have to follow this pattern, all right? As you see, there are 3 options here. Which option should we follow? To decide it, we need to know the value of immediate part, I value, let's say. All right. So I value, as you see here, it is 1. So it means immediate value exists. All right. 1, it means immediate exists. So it exists. Therefore, we'll follow the first structure here. Let me write it above. So this is condition. This is operation type. This is I value. This is CMD value, which determines which operation should we use. And by the way, 1101 is a move operation. So 0. So this 1 bit represents S. If it's 0, it means we don't use S suffix. But if it's 1, in that case we use S. By the way, what's add? For example, add S, adds. What does it mean? In that case, we are updating condition flags. But if it's 0, we don't update them. All right, here it's zeros. So since it's move operation, so we don't have even moves. Let's say operation. So these four digits will be Rn, the first uh, source register. So the second four bits will be Rd. It means destination register. All right, and this will be rotation, and this will be immediate. So what's rotation? As you see, there are 8 bytes in immediate part. If these are full, in that case, if you want to have more bigger value, let's say bigger values, in that case, we'll use rotation. All right. Here, all of them are zero, so no need. So we'll not need even in this homework, I believe. So as you see, our instruction will be move RNs. In move operation, we don't need first source register, all right? So we don't need even R0. But we need destination register. As you see here, it's 1. RD is 1, all right? Converting decimal, you'll see that it's 1. So R1 will be what? Will be 0. How did I know that? From here, all right? Immediate value is 0. So we have already get our first operation instruction, let's say, which is move R1 0. And it is based on this structure. I want to just remind you, as you see, condition, operation, I, S part, CMD part, first register, source register, destination register, and second source can be 3 options here. Since I is 1, we'll use this rotation and immediate value. All right? So let's go ahead. As you see, we have one more uh, hexadecimal value here. And if you look at here, the first 4 digits are the same. All right. So we can just copy this and paste it here. All right. Then there's a difference here. It's 2. It's 2. And these 2 digits are same. And the last digit is different. All right. Good. So if we analyze this code, this binary sequence, so this means unconditional. As you see, this will be data processing operation again. It's because of till here it should be same, guys. All right, till here it should be same. All right. So data processing, immediate value exists. Again, move operation. All right, and I is here, CMD value is here, S is here, and this is Rn. Good. So what changed here? RD changed. All right. Rotation is the same, 0, 0. And immediate value part, what changed? Immediate value is changed to what? 10. All right. So it means our operation will be move destination change R2, and immediate value change, it will be it is altered, so it will be 10. All right. So this is our second operation instruction. So let's move to the next. As you see, again, one more instruction is the same with others. I mean, not exactly the same, but there is the same part. So we can expect that this operation will be move operation. But what changed here? As you see, the fifth binary. Fifth binary is RD. So RD will be 3. How did I know that? So 3, it's 3. Even I don't convert. R3. And immediate value, how did I determine the last 2 digits? 0, 0. It's 0, 0. So it will be move R3, R3, 0. So even we didn't convert. All right. We converted, but I mean, we don't need to rewrite it. All right. Good. And again, one more move operation. So it will be move R4. How did I know that? It's because fifth is RD is 4, and the last two is immediate value, it's 5. So 5 is 5. So this is clear too. As you see, I don't want to lose time. I don't want to waste time. Just all of them follow the same pattern. So we complete it. But if you look at here, you will see that there is a difference. There's a difference here. All right. So we need to convert it binary initially. So it will be 1, 1, 1, 0, 0, 0, 0, 5, 3, again 5, again 0, 0, 0, 0, 0, and 4. All right. So how many? 6 digits. Perfect. Now let me take it and put it here. So the first is 1110. It means unconditional. This means unconditional. So we don't need, this is unconditional. We don't have less than, we don't have greater than equal. It's unconditional. All right. And we need to pay attention here. Oh, it is again data processing. So 0, 0, it means data processing, DP. Since it's data processing, we'll follow this pattern. We'll divide it like this. You see how I divide? So CMD value changed. So we don't have I. There's no immediate value, no I, no immediate value. It's 0. We have CMD this. We have CMD this. We will need table to look for that value. As you see, these are CMD values. 0, 0, 10 is, it is equivalent to subtract. Good. Subtract. Subtract. Good. Subtract. So 1, it means we'll use S. So we are updating flags. All right. It will be sub S. Good. Since we don't use immediate, so we should be careful after this. All right. We should look at here. No immediate value. So I is 0. We have 2 paths to follow. So which one should we choose? To decide it, we have to divide like this from the right hand side. Divide, taking 4 bits from right hand side, then coming to the 5th bit. If it's 0, it will be registered. If it's 1, it will be registered, shifted register. All right. Let's look at here. Let's look at here. Where? Okay, I found it. So 3, it was 4. I forgot again, guys. Was it? It's not 3. It's 4 bits, as you see. Indexing from 0, it means there will be 4 bits. So 5th bits, yes. So it will be 0. It means it's not register shifted by register. It's register 1. All right. So this will be 1 minute. It means this will be RM. RM means second source register. This is just constant. And then this will be shift. Let's say it's called shift. What does it mean? If it's 0, 0, it means shift type is logical shift left. All right. If it's 0, 1, logical shift right. So let me write it here. Shift 0, 0, it means logical shift left. All right. And this part represents shift amount 5. This is called shift amount 5. It is 0, 0. It means will not shift anything. All right. Will not shift anything. It's 0, 0. So what about here? This is Rn, and this is called Rd. All right. Let me bring some here. So RD. Okay. I hope it's clear. I'm not confusing you. So as a result, we have which operation? We have subs. Destination is 5, R5. First source is 3, R3. And we don't have immediate value, we have register. So there will be no shift. It's because shift amount is 0. And its RM is R4, isn't it? It's R4, exactly. So our instruction will be like this. So that's it. Subs. So it means we are subtracting R4 from R3 and store it in R5. All right. Next operation is even it's more different. It starts with B, but this was starting with E. It means it will not be data processing. It will be something else. All right. Initially, let's convert it to binary. It will be 11, isn't it? And it will be 0, 0. It will be 1 minute. 0. It will be 8. Okay, 8 will be something like this. 0, 0. Again, 4 zeros. Let's say 4 zeros, and at the end will be 2. Okay, all right. Yes. Well, let's take this and put it here. So this is condition. Which condition? Let's look at here. Do we have the table here? Did I put it here? It seems I didn't put it here, but I can find it for you from here. 1 minute. From presentations, you can find. So this is condition 10, 11. LT less than. Okay, it's less than operation. Less than operation. Between LT less than operation. So condition is clear. So we have to be careful here. Again, it is data processing. I failed in my decision. I said that it can be different. It may be different, but it wasn't different. It's the same. Data processing. So good. Now it's clear for us which pattern to follow. All right. We have to take 6 bits here and divide them like this. So it means no immediate value. It's 0. And CMD value is 100. Let's see. It means 0, 100. It will be add operation. Good. It will be add operation. Add operation. So no S, no S. So no immediate value. We have two options. Whether it is register or register shifter register. So what should we do? Already. It's because we have already did similar exercise here. So we should divide like this, isn't it? As you see, here it is 0. It means it will be register, not register shifted register, all right? So we have, what do we have? We have rn 0, r0. This is rn. So we have rd, next is rd. Again, it's r0. So this is shift amount 5. It will be no, it means there will be no shifting. So logical shift left, but doesn't matter. Shift amount is 0. It means no shifting. So this is constant value, and this is RM. RM, the second source register, is R2. Good. So this is clear. Add what? It will be R0, R0, R2. So this is our operation. Actually not. We should add LT. Add LT, R0, R2. So this is our Data processing operation adds. All right, we are just, what do we do? This is conditional, so we are updating flags also, since it's conditional. All right. So next, so let's look at here again. It will be 1 0 1 1, isn't it? Again, like this, three, one more three, and zeros, zeros, and one. Good. Now let's take this and put it here. Scott will divide it according to the relevant pattern. So it will be conditional. Will determine taking these 2 bits. Okay, this is data processing. Data processing conditional will be what? 1011 was LT. Again, LT condition. So we have to follow this pattern again, dividing them by this. We have immediate value, immediate we have. So we have this CMD value, which is what? 0, 100, which is add again, add operation means add, no S. So immediate exists, therefore we should follow this pattern, isn't it? This part will represent immediate value, this part will represent rotation. All right. You can refer to these tables. All right. So let's go ahead. Uh, good. We have these 0 0 0. Good. And then what do we do? What do we do? This is Rn. Rn is R3. So Rd is again R3. So it means what do we do? Just writing. By the way, yes, what do we do? Just we're writing add less than R3, and again R3, and we are adding what? 1, just 1. Perfect. This is our instruction. Good. We continue. We are going ahead. So let's convert this again. You know how to convert. All right, 11, it should be 11. It should be 10. It should be 15. All will be ones. All right. 5 ones. I mean, 5 times this, 15. And 11. Now, let's take this value and decide. So, this is LT. This is clear for us. So we need to divide like this. 1 0. So this operation is branch operation. All right, branch operation. Keeping your mind, 0 0 is data processing, 0 1 is memory operation, 1 0 is branch operation. There is no 1 1. All right, no 1 1, no 1 1 opcode. All right, good. Even let's like make it like this. So since it's branch, we have to follow another pattern, which is this. So there will be 1L, L. If it's 1, in that case, it's branch with link. If it's 0, it means only branch. And there will be 24 bits here, which represent signed immediate operand. And this is 2's complement, all right? 2's complement value. Signed 2's complement immediate field. And it will use it to specify an instruction address relative to program counter plus 8. Program counter plus 8, it means what? It means R15. Yes, R15. Good. We are here, all right? So as you see, it's 1 0. It means branch without link. Without. All right. And this part is 24 two's complement immediate value. So initially, what should we do? We should, to find this value, as you see, it's negative. So we should how do we convert it? Again, we are finding two's complement. To find two's complement, initially we are reversing ones to zero and zeros to one, replacing them. All right. So it will be like this. Let me count them. So how many? How many? How many? 3, 24, 21. So 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19, 20, 21. All right. So 1. Okay, good. 3, 6, 9, 12, 15, 18, 21, 22, and 24. Yes, it's true. Then we need to add 1 plus 1. All right, so it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So this value, it should be this value. What does it mean? It means branch less than, let's say loop 1. This is kind of name. And this loop 1 is located where? It is located program counter plus 8 minus 4 times 5. Why minus? It's because it's negative. And this value is 5. But why did I multiply it by 4? It means it is word. It's called word size. All right. One word is equal to 4 bytes. Therefore, we are multiplying it like this. It means it will be program counter plus, minus 12. All right. We'll decide when we, let's say, construct the code. All right. Next operation. By the way, let me look at the timer. Oh my god. But I want to explain all details, guys. I'm sorry. Um, let's go ahead. Let's go ahead. Again, this will be what? It will be this. So 11 and this. So 4, 5, and 6. Good. Now, let me take this again and copy paste it here. So for first is, it means unconditional. Yes? So we need to pay attention. The next 2 bits, as you see, it is branch operation. All right? It's branch operation and it's branch with link. It means branch with link. So we should take this value, put it here, convert it 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and it will 24. And if we add 1, it will be something like this. So the result will be BL, let's say loop 2, and it should be program counter plus 8 minus 1 times 4. All right. So as a result, this value will be equal to program counter minus, not minus, but plus 4. So next, this operation, again, let's convert it. It is a 14 EF. Yes, it should be something like this. 5, 2. D is what? It's 13, isn't it? It is 13. It means it should be something like this. 8, 4, and 13. Yes. So 13, again, this 0, 0, 0, 0, and sorry, this. All right. Now, this is unconditional. It is explicit for us. All right. It is unconditional. Unconditional. And if you look at here, operand type is memory instruction. So it will memory instruction. We need to follow another pattern. Look at here. This is pattern for the memory instructions. As you see, condition, 2 bits operation type, and then 6 bits for function. We'll talk about them. Array, RD, and source. If immediate exists, 12 bits for immediate. If it doesn't exist, I bar will be 1. It's of complement of I, immediate value. It will be shift amount 5, shift 1, and array. All right. So now, initially, let's pay attention to I bar. Is it 0 or 1? Is it 0 or 1? I bar is 0. What does it mean? It means immediate exists. All right. So 12 bits will be for immediate. We will RD, RN, and this will be for all the stuff I will tell. Okay. Now, this is I bar. This is P. This is U. This is B. This is W. And this is L. Isn't it? Am I right, guys? Yes, exactly. Let me even put more distance for clarity. So it will be something like this. Now, let's decide following this pattern. I decide whether it's immediate or register. You decide whether it's subtract or add. If it's 0, it's subtract. It's 1, it's add. Let's look at U. Is it subtract or something else? Add. Something else, I'm adding. All right. So U is 0. It means it is subtract. All right. Now we have pairs. Which pairs? We have PW pair and we have LB pair. PW and LB. PW and LB. Let's look at here. PW is 1, 1. What about 1, 1? LB is 0, 0. Isn't it? Am I right? Yes. It's something like 0. Yes. PW is 1, 1. What's 1, 1? It's a pre-index. And 0, 0 is store instruction. So we have two types of store, load, register, store to register. So let me find it. It will be pre-index. Of course, store for load pre-index. Store, let me note it here, pre-index. And let me note it here that it should be store. All right, good. So this part is clear. This is Rn, by the way. Rn is which register it will be 13, and our D is R14. You know that R3 is SP stack pointer register, and this is link register. All right. So operation will be store R14, R13, since it's subtract 4 and it's pre-index, it will be something like this, isn't it? Yes, this is our memory operation instruction. I hope it's clear for you. All right. Now continue. As you see, this will be move operations. If you look at the first four digits, they are same here as you see. E3A0. So we have move operations again. A0. Okay, let's look at here. So let me convert it short, like it will be move. So this is RD, isn't it? R4, how much? 15. So 15. This is clear. So we'll not lose our time here. And again, here it will be, even let me write it on the same page. Move R5, which value? 10. Perfect. Now we did also this. Now next, 3 left. And if you look at here, what will happen? Let's convert again. It will be what again? 0 0 0 8 5 6 0 0 0 and 4. So now let's analyze this. Again, it's unconditional, it's obvious. It is data processing operation. How did I know that? This is 2 bits. So since it's data processing, I have to follow this pattern here like this. So 0 0, it means immediate value doesn't exist. CMD value is this. So S, no S. So since there is no immediate value, again, I have to be careful here. 4 and dividing like this. So since it's 0, again, it's shifting. I mean, it's not register shift. Register by register, it's just shifting with immediate value. Say, but since it's shift amount, this is shift amount. Shift amount 5 is 0. There will be no shifting. All right. So this is RM. We know this. This is RM. Let me write it. RM. So this is RT, and this is RN, isn't it? Yes. Good. Now, what do we do? Just we know that. So what do we know? 0, 100. This is add operation, if I am not mistaken. Let me clarify and then continue. Right? Yes, this is add operation. This is add operation. So we'll write add without s. Destination is R6. First source is R5. Second source is R3, isn't it? Yo, it's R4. It's R4. So that's it. R5, R4, and this. Unconditional. Good. The last two. Let's decide what they are. All right. Again, unconditional, since it starts with E. So 0, 0, as you see. Let me even decide like this. So this is data processing. Since this is data processing, I have to be careful. So 5. So if I do something like this, I hope it will be clear for you. Data processing, not like this, I'm sorry. It should be something like this, right? Yes, did 5, then it will be 3, 3. It will be 5, 0, 0, 0, 0, and 4. So we don't have what? Immediate value. We have S. Since we don't have immediate value, we have to be careful. Again, it's 0, so it will be what? Only register type, not register shifted by register. All right. Register is shifted by immediate value, but shift amount is 0, so no shifting will happen. This is RM. So let me write 0, 0, 10. Which operation is it? Let's say this is subtract, unconditional subtract, subs even. It's because we have S here. All right. All right. Let me plug in my computer. Good. So we have RD, which is 5. We have first source register R3, and we have second source register R4. So perfect. This is ready too. Now we are fast even. Again, since it will be unconditional, all right, we are fast enough. This will be 10, 10. And if you divide like this, you will see that this is branching. Good. So this will represent sine 2's complement immediate value, isn't it? 1, 1, 1, 1, 1. Let me write separately. So 5 ones, let's say, and 9. So it will be something like this, isn't it? Yes. And it will be branch without link, since it's mentioned that it is written that after 1 value is 0. All right. 1L. You remember this structure? 1L. You see? So it's 0, it means without branch. Without link, I am sorry. So what do we need? We need takes this value and converts it. So if we convert 1, 1, 1, 1, and what we'll get here, 0, 1, 1, 0. And if we add 1, it will be this value, isn't it? So branch without link to somewhere. Actually, somewhere will be loop 2. Let me write it loop 2. I will explain. But where exactly? Where is it? Program counter plus 8 minus, this is 7. 7 times 4, isn't it? And if you calculate, what will we get? We'll get program counter plus, not plus, minus 20. So perfect. We completed all the stuff. And let's look at our code here. Yes, this is our code. Let me take it. Okay. And let me put it here. All right. So as you see, we start move R1 0, move R2 10, move R3 0, move R4 5, and let's say we don't have this for now. We are writing these operations and BLT loop 1. All right. Let's look at here. BLT loop 1. BLT branch. If less than. Oh my God, where is it? Where is it? I hope it will be somewhere here. It was here. I didn't highlight it. I didn't highlight. So BLT loop 1. Okay. Program counter minus 12. All right. If we are here, it is minus 12, 3 instructions back. 1, 2, and 3. It should refer to here. All right. So it will be loop 1. All right. Loop 1 will refer to here. Then BL loop 2. We assign it like BL loop 2. Where is it? Is it? It's here. Program counter plus 4. Program counter is if this instruction is executed plus 4, it means this instruction. So therefore we located it here. It means we are on the right way. All right. So storing operation, move, add, subtract, and branch. There are some problems in this code. All right. What are they? What are they? Initially, there are uninitialized registers. For example, R0 is uninitialized register. So we need to initialize R0, isn't it? And even one minute, we need to initialize it, but even we don't need R1 here. If you look at, we don't use R1. So I would say let's change, remove R1, and write it here R0. All right, we need to initialize it. So move R to a 10, that's okay. Adding R3, 0, R4. But consider that starting from R4 to R11, they're called call save registers. All right, when we are using them inside uh, inside branch, we need to store them in stack and then loading back. All right, so we need to save them, let's say. All right, so even what would I suggest? I would suggest replacing these values like rt is 10. Instead of r2 I would write r1. Where is 2? I will write 1. For example, here I will write r1, r2. Do we have r2 here? No r2. So instead of r3 I would write r2, 3. For example, I write 2, 3. I will write 2. I will write 2. Is there any 3? Yes. Or 2. And for the R4, I would write R3. So 4, where I see 4, I will write 3. So 4 will be 3. Here 2, 4 will be 3 here 2, and it will be 3 here 2. Good. Now, we don't use R4, we are using R3, but again, still we are using R5 here. But we didn't initialize. Anyway, if you use that, we should, let's say, store it. But here, actually, if we didn't, it will not be a problem. Uh, let's not lose time, actually. It's already 49 minutes. So let's look at here that I already completed all the stuff here. As you see, we don't need here. Yes, we don't need it because we don't kind of give initial value it's and changing it. All right, it's initialized, just we are giving some value. Overwriting, this is called overwrite, by the way. Yes, overwriting condition flags are set, is set. Yes. um, by the way, I didn't here do something. Okay, I didn't add r0. I didn't initialize r0 here. Why? It would be better to, so I didn't change values here, by the way, but it would be better to initialize r0 to 0. All right, initializing. Uh, no, 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 no. Okay, this is okay. This code is just okay. Now I got it. This code is given code, but we need to do something else. It is here. Let me take it. And yes, below suggested correct form. Let me copy and paste it here. And then let's not lose our time. I have already done all the stuff and just explaining over this code. Initialize this, changing this. I will explain this part. Be patient, please. Yeah, as you see, we don't need to storing R5, although it's called a saved register, but I mean, there's not its. I mean, there's not its initial value. All right. So adding if less than, adding less than one, and branch less than loop one. So there will be 5 times looping here, and then it will come to branch link loop two. Then what did I do? By the way, Th- there are some problems. One of them is initializing problem, and one more initializing problem is initializing link register. We should show where to um, not register, I'm sorry, stack pointer. Stack pointer should refer to some memory location, stack memory, all right? And usually it's this address. You can change this address, but usually it's this, all right? And we initialize our 13 too. Besides that, what did we do? Besides that, okay, we should, if you look at here, there's infinite, not here, but let me show it here. If you look at here, there is an infinite looping here, infinite loop. This also will crash the program. So we need to add something to stop the program. So CVC2, this will end program. But here we can see CVC exception. So to handle them, I learned from GPT that we can use this code to for SVS, I'm sorry, SVC exception handling. All right. So this is uh, clear too, I hope. BL loop 2. So we are branching loop 2, but also taking the address of CVC2. All right. So link address contains this address. And here, as you see, we are using our 4, 5, 6. All right. So they're called safe registers. For example, R5 has value like this, initial value. So R6, I'm not sure whether it has or not, but still. So we should save this register, especially after branching link. So this is important, branch with link. In that case, when we are branching with link, we should save call save registers. Store multiple full registers with full descending order. All right, this is called like that. It means will will it means will store starting from R4 till R6. I mean R4, R5, R6. And what do? We store them in stack, and after that, we can override R4, R5, R6, and doing some operations here. After finishing, finalizing of operations, we should load them back, all right, to registers, and bxlr branching back. LR contains this address, so it will come here and will end the program, all right. So this is better form of the code, and this code will not crash. Compile and load, step into. As you see here, R2 is increasing. When it reaches to 5, it will exit the loop 1. So now it will exit. Look here. Step into one more time. So it exited the loop and branch with link. So it will branch to loop 2. You see? Branch, push R4, R5, R6. then doing some operations, then popping those values, branch back, LR, we are here, CVC. So that's it. And even if we click step into, it will come back here, all right? And like it will restart, let's say, all right? So that's it, I hope. We did all requirements. Let me look through. So I completed all this stuff and discussing demonstrative understanding. Yes, I just explained all the stuff here. This is, by the way, what my README file that I explain all details here. Then this is code that we found and crash factors like pushing R14 to the stack here, push popping this part. But we should also pop it, all right? Pushing and then pop. But even we don't need it, all right? It's because we don't need even to store LR as a stack. It's because we don't change it, all right? So one more thing, infinite loop, not storing call save registers in the stack. Yes, yes, that's it. So I hope everything is clear for you. I try to do my best. If you have questions, you can write in comments. So see you in next videos, next topics.